confidence intervals. And this is just the same stuff we've been talking about with plus or minus 2 standard errors, plus or minus 1 standard error. A confidence interval is the average plus and minus a z-value, which tells you how many standard errors you're going up and down, times the standard error of the mean. You can write it, the standard error, different ways. This is just the official version of what we've been doing. So the z tells you how wide the confidence interval is. It tells you what the bet is, whether you got 95% or 68% bets. All right, and we can make any bet of any probability. All we need to do is look up the right z value. So this is the official confidence interval formula. When you do a sample for a mean or a proportion, for a proportion it's just we replace the standard error with the standard error of the proportion. 68%, 95%, 60%, 80%, whatever the bet is, that's called a confidence interval. And it's got a lower limit and an upper limit. If we do the 95% confidence interval, we go 2 standard errors up, 2 down. 2 down makes the lower limit, 2 up makes the upper limit. These are always symmetric because they come out of a normal distribution, and we're just doing the plus and minus 2 standard errors. So that would make a 95% bet. So whatever value is in the lower limit, that's here, and the upper limit is there. One problem with this, and it's something that is difficult to explain to people, is that confidence intervals are symmetric and decisions aren't. If you're buying a car and you get the car for really cheap, that's good. You're happy about that. What you don't want to do is pay too much for the car. You're more concerned about the upper end than the lower end. So that if you got a confidence interval on the price of a car, if you're at the low end, good. You don't care. You pay them a little more than that because you're getting a good deal. It's the upper end you got to worry about. I used to do timber sales. You're buying trees on a piece of land. You don't buy the land, you buy the trees. And you send somebody out there and they measure this and they estimate the number of cubic feet, the amount of carbon, whatever it is on these trees. The traditional way this is done is somebody puts up a timber sale and different companies come there and they're going to bid on this. So they actually walk in with an envelope and say, here's my bid. If you got it cheap, you didn't care. That's good. If you bought it and you paid much less than you think it was worth, you're happy about it. If you paid more, that's what you're concerned about. In particular, if you paid more than what you got out of it, then that's not good. Right? The problem with these things is we usually don't know the real answer. And when they do a timber sale, until somebody actually goes in and cuts trees, nobody knows what the answer is. And by the time they get around to that and they haul it off to a mill, the original purchase is so far away from the result that nobody looks back. Everything we got is a bet. And we may be concerned about the low end or we may be concerned about the high end, but the confidence interval, as stated, is always symmetric, so that there's a real disconnect between statistical practice, say, or the terminology, and what we're trying to do. Somebody buys a company. They're going to buy, what's the online deal? Paramount Plus, So they buy it, and there was a competitor, and the price kept going up. Well, finally, one of them drops out, the other one buys it, or is going to buy it, and they won't know for a very long time, if ever, whether they overpaid for that. It's difficult because it's all a bet, and that's the only thing we can do. We usually don't know the answer. We won't find out whether we were right or wrong until much later. All we can do is bet on it. We don't know. All we got is a bet, and we got a lower limit and an upper limit, and this is what we can say about it. What you do with it is a whole other game. So I can tell you how to do this, but not what to do with it. Suppose we have fish. So we get 30 fish, and our mean is a length of 42 centimeters. We get these fish, we get 30 fish, we get the mean, and we get the standard deviation. And the standard deviation is 20. Now we do the standard error, which is equal to 20 divided by the square root of 30. 3.65. For this, the average is 42, and this is centimeters. The standard deviation is 30. Standard deviation is 20. That's in centimeters. And the standard error, 3.65, and that's in centimeters. All of these are in the same units because I need to add and subtract these things. For a 95% bet, we have the average plus and minus 2 times 3.65. So it's 42 plus or minus 7.3, it says here. So if I go down 7.3 centimeters, that's the lower limit. I go up 7.3 centimeters, that's the upper limit. And those two are respectively 34.7 and 49.3. Lower limit and upper limit. And this is just add, subtract. That means that the true average length is between those two values with 95% odds. The true average is in there or it's not. I don't know. That's my bet, 95%. This part, the z-value times the standard error. It's called the margin of error. And when they do proportions, they call it the margin of error. For a mean, it's the margin of error, but it's not explicitly stated. This is the bet, odds. And this comes from the sample. I do the sample, I get a mean, I get a standard deviation, I get a standard error of the mean. I don't get to choose any of those. The only thing I can choose on a bet is what my odds will be. If I bet on 95% odds, I got a wide interval. And the real answer could be anywhere in there. If I bet on a 50% interval, and I need to look up a new z-value that would give me 50% in the middle, I've got a narrow interval. Which would you rather have, this one or this one? They're the same thing. What changed between 95 68, and 50. Got a pencil, something you can hold up? Get your telephone, anything, so you can look at the width. Here, my cone of vision, so to speak, is like this. How much of the pencil can I see? As I move it out, I can see more of it. It's just further away. It's the same length. So when you're looking at confidence intervals, the only difference is how far you can see. The same length for all of those things, I can see different widths. So that the only thing that's different is the odds. And this is a very difficult thing to explain to somebody who's betting money on something, that it doesn't matter what odds you use, all the odds R is a different multiplier for the data you have. The margin of error, this Z times the standard error, really depends on how much of it you want to see. Your standard error is done. You've got a sample. You can't change the mean. You can't change the standard deviation. Those are estimates of the population parameters. Even the standard error of the mean is an estimate of a population parameter, and you can't change it. You've got the result. What we're looking at is how much faith I want to have in a value. Here's minus 2 standard errors and plus 2 standard errors, and there's the middle. 0 standard errors. This is the average. This is the average plus 2 standard errors. This is the average minus 2 standard errors. If I come in 1 standard error, average minus a standard error, that's 1, minus 1 is the average minus a standard error, and all I have are different pieces that I can bet on. If I wanted an 80% bet, where would the 80% be? Draw a picture. Draw an 80% bet. Where is it compared to the 95 and the 68? Yeah, kind of in here somewhere. 80% bet. Where's the 70% bet? Squeeze in a little more. 50% bet. Here's 70. This is 68, so 70 is right outside of that. 50 is going to be inside of it. I can make a 20% bet. I've got a 20% chance of trapping the true average in an interval this wide. From a perspective of the interval, it is the same as this one at 95%. It's just what I want to talk about. So instead of treating these things as fixed symmetric intervals, the thing to do is to look at it in pieces. What's the chance that the true average is all the way out there, out in this range, outside of the 98 or the 95 on the high end? 2.5. So I've got a 97.5% chance that it's back here. So what do I want to bet on? 2.5 or 97.5? Yeah, I'm going with a 97.5. If I'm trying to protect myself on the low end, I want something way down here. If I'm buying something, I don't want to pay more than I get for it. So I want to make sure that I'm safe on this end. In this spot here, I'm perfectly good betting on the 2.5% on the low end. Depends on where are you going to win or where are you going to lose. And this gets into psychology. Most people will limit their losses rather than try to maximize their gains. You go to a horse race, what horse are you going to bet on? Yeah. What horse do most people bet on? Yeah, the favorite. So you bet $2, you get $2.50. It's good. You didn't lose. What horse do you want to bet on if you're going to make money? If you want to maximize your gains, you want the one with a limp. Because if it wins, you're good. Right, so all of this stuff is fact. This is the way it's set up. The way it's used is an entirely different deal. This deal with the average plus and minus the margin of error. And the margin of error includes how many standard errors up and down you're going. If I take the margin of error, divide it by the average, multiply it times 100, I have converted the confidence interval to a percentage. So rather than saying this many standard errors up and down, I'm looking at it as a percent of the mean. This goes back to standard deviation over the average. All I can do is find that out. The standard error times the z over the average is just a different way to look at it. So before I had the average was 42, the margin of error was 7.3. That's a 95% bet. Or 7.3 divided by 42 times 100. What is the percent bet as a percent of the average? You divide the 7.3 by 42, what do you get? Well, 7.3 over 42 is about 1/6, which is about 16%. So instead of saying an absolute number, I say I'm within plus or minus 17%. The true average is between the sample average plus and minus 17% of the sample average. And then I have taken out the units. I've taken out the centimeters because the margin of error is in centimeters. The average is in centimeters. And I'm left with a percent bet. And this is the way most bets like this are stated. Rather than saying 7.65 centimeters plus and minus, we say plus or minus 17%. With 95% odds. The percentages, we got percents on percents. So you got to watch that. But it's a 95% bet that the true average is within 17% of my sample mean. When I get to that, I have another way to look at all of this. Here is this is a 95% bet, and it is at plus and minus 17%. What's the 68% bet? $17 is 95%. What's the difference between a 95% bet and a 68% bet? How far out do I go for the 95? 2. How far out do I go for the 68? Plus or minus 1, so that the 68% bet is at plus and minus 8.5%. This is the advantage of the 68 and the 95. One's twice the other. So if I know one, like the 95, I take half of it and I get the 68. And you can actually draw a graph, and basically it's a straight line. And any bet along this line is the same bet. This is the bet at 95. This is the bet at 68. If I come back here to 50, it's going to be there. And if you do interpolation and so forth, you can draw a line for this. So once I have this as a percentage, all I have to do is manipulate how much I go up and down because I've got a percent. The 68% is the kind of the foundation. It's one up, one down. One margin of error divided by the average. 95% bet, I multiply that by 2. The 50% bet, in fact, is 0.7 standard errors up and down. So that all of these things are the same. Every bet on this line, every confidence interval is the same. Most people, when they are asked for a result from a sample, you say, well, how close do you want to be? With what odds? They will say plus or minus 10% with 95% odds, because it sounds good. Well, what is the 68% bet if I have plus or minus, and these are plus and minus, so you go up and you go down one margin of error, plus or minus 10% with 95% odds? What's the 68% bet? 5. This is a multiplier of 2. This is a multiplier of 1. A 50% bet is a multiplier of 0.7. What is the 50% bet? 0.7 times 5. This is a 3.5% bet, plus and minus. So those are the important things. Right. All of this that I have used so far has been this Z. Z times the standard error. That's the margin of error. This is not absolutely correct, because the Z uses a normal distribution. This is actually where I should use a T distribution. All right, the guy who invented all this stuff, he used normal probabilities. He was quite happy with it. The master brewer, a guy named Gossett, the master brewer of the Guinness Stout Brewery in England, was a statistician. And he was experimenting with different kinds of ingredients for making Guinness Draft, Guinness Stout. But he had only very small sample sizes. So he didn't think that the bets he was making with the normal distribution were accurate. He didn't think his bets were that good. So that Mr. Gossett published a paper under the name of student. He called this distribution a T distribution. So that we have student's T distribution, and what we actually have in these things, the official version, is T times the standard error, not Z. The difference is the T distribution is wider and flatter than the standard normal. The mean is still 0, but compared to a standard normal distribution, I actually have a picture here somewhere, don't I? The T distribution for small sample sizes is flatter and wider, so that instead of 2 standard errors up and down, depending on the sample size, we might have 2.1 standard errors up and down. So that the T distribution is wide, and if the sample size is small, it is very wide compared to the standard normal. Because Mr. Gossett was working with sample sizes as small as 5. Because he's making beer. So he's got small sample sizes. The T distribution depends on the degrees of freedom. You remember the pencils in a box? 5 pencils in the box. First person gets to choose 1 out of 5. Next one, 1 out of 4. Next one, 1 out of 3. Finally, you get to the last person. There's no degrees of freedom left. Degrees of freedom, in this context, degrees of freedom is equal to n minus 1. So that if I have a sample size of 30, the degrees of freedom is 29. Right, there's different things that this comes into much later. But this is why, for the standard deviation, we use an n minus 1 divisor instead of an n divisor. Here, hopefully, this is the difference between the standard normal and the T distribution. For a sample size of 5, which is small, this is right in with Mr. Gossett's sample sizes, instead of 2 standard errors up and down for a 95% bet, I would have 2.78 standard errors up and down. So instead of 2, I multiply by 2.78, which makes my interval wider for the same level of bet. And for the 68% bet, I'm using 1.13 rather than 1. This is, to me, completely useless. But this is the way everyone has been taught. Instead of using Z of 2, you would use Z or T of 2.78. As you get larger in sample size, the degrees of freedom becomes less important. Instead of sample size of 5 with 4 degrees of freedom, if I get to a sample size of 30, I have 29 degrees of freedom. And if you look there at 30, instead of 2, I'm using 2.05 standard errors up and down for the 95%. And for the 68%, I'm using 1.01. I've never worked, well, I have. I worked with a sample size of 3. This was ludicrous. No, not to them it wasn't. These were wood guys. They were looking at the relative strength of tree rings over the year. Summer wood, spring wood. The spring wood is wide and light colored. You look at a pine, 2x4, you can see the rings. There's a harder part, a softer part early in the year. They had split these things into 3 pieces. They took a tree ring, split it into 3 pieces, and were looking at the relative properties, the strength of each one of these parts of the tree ring. So I was analyzing their stuff using a sample size of 3. Otherwise, my sample sizes were 2,000, 200 minimum. The difference between the Z and the T value at a sample size of 200 is immaterial. The difference at 25 is immaterial. But we're stuck with the T distribution. Confidence intervals aren't done with Z values, really. They're done with T values. Although the difference for any practical purpose is immaterial. So to the point where I don't even like to talk about the T distribution, except that's the way people expect it to be, because it's been hanging around for so long. So here, this is a T table. And we have a different multiplier for every sample size. So that as you go down on this left column with degrees of freedom, this is n-1, and we have different tails cut off because we don't have a nice, clean, standard normal distribution anymore. It depends on the degrees of freedom. So that the area in one tail, here's 0.025, it's in the middle. You can see how many standard errors up and down you would have to go for a given sample size. So here is a sample size of 2. And you would have to go up and down 12.71 standard errors to get a 95% bet. Sample size of 2 is ridiculous. Look as you go down the table in the degrees of freedom. As you get more and more degrees of freedom, bigger and bigger sample sizes, by the time you get to 30, we're down to basically 2, which is what the standard normal will give you. We don't really use a Z, we use a T value. Using the T value makes no difference. But that's what people expect to hear, because it's been ingrained in statistics education for the last 150 years. As a practical matter, always use 2 for 95%. You can't go wrong. And very few people make anything other than a 95% bet. So if you only remember 2 standard errors up and down, you've got most of statistics covered as far as most people are concerned. All of this stuff has history that we drag along with us. Gossett was the master brewer at the Guinness Stout Brewery, so don't think that statistics never gave you anything. But he left us with this student's tea because when he published it, he couldn't use his real name. So he used the name student. And that's why it's called the student's tea distribution.